We will continue with our discussion of helicopter performance. In the previous series of videos, first we looked at the vehicle in hover and vertical flight. We got an expression for how much power is required for a vehicle to stay in hover and also in vertical flight. Then in the second set of videos, we looked at the forward flight. We found that the power is coming from the induced power because we are accelerating the flow, pushing it down to produce thrust. That's the induced power. We have parasite power because we are dragging the fuselage with us. The fuselage has got a certain amount of drag force. So the drag force times the velocity is the parasite power. Then we have profile power because we are spinning the rotor and the rotor has got skin friction drag. There's a profile power. We haven't done any examples yet, so we'll have a separate set of videos on worked out examples. But right now, let's look at how do we use this information to assess the performance of a vehicle. So the vehicle performance is done in the following perspective. We want to know how high can we fly, either a absolute ceiling or a service ceiling. We need to know. We often want to know how fast can we go, what is the maximum forward speed, how far can I travel, which is the range, how long can I stay up in the air, which is the vehicle endurance. So these are some of the things that we are going to be looking at in this particular series of videos. You have to start with the engine. So the engine performance data is usually available from the manufacturer. They may give you, for example, how much fuel is being burned, what are the horsepower, what is the maximum power you can get for takeoff, for example, for a brief period of time. They may give you maximum continuous power. They may give you at a different altitudes, or we would use our curve fits like we used to do, such as density ratio, to scale information from one density to another density. But what happens is in the case of helicopters is the engines are buried inside the fuselage. So you have a large inlet through which air is pumped through, and you have usually a large outlet or a duct through which the hot gases are coming out. So once you install it inside an airframe, things dramatically change. Not dramatically, but they do change. Therefore, we need to have some estimates of installed power losses. Initially, these would be guesstimates or empirical formulas. Then later on, from flight testing of a helicopter, they will get a better idea of how much power is available at various altitudes and various conditions. What are some of the losses? As I mentioned to you, there's a long duct through which you suck in the air. By the way, some helicopters will have the engines outside the fuselage, but others may have inside the fuselage, depending on the situation. There is a loss, total pressure losses take place in the inlet. We also may have particle separators, either screens or some other mechanisms by which separate out the sand, for example. They all produce losses. Exhaust duct, if it's long, then it may produce some losses. If you have infrared suppressors, basically these mix hot air and cold air and then come out, the warm air is coming out. Then these infrared suppressors can also produce losses. If you re-ingest the hot gases, remember you're hovering, sometimes or maybe sitting on the ground, the way the engine is spinning, then you may ingest the hot gases back in. You may get an increase in the inlet temperature. So thermodynamic efficiency is 1 minus T inlet by T exit. So when T inlet is high, you're going to lose efficiency. If you're bleeding compressor air or compressor power, any accessories, all these things cause a loss of power. Therefore, the net power that's supplied would not be what the manufacturer gave you. It would be less than what the manufacturer has specified. One thing we have not talked about that we should keep in mind is sometimes the download, when the wake of the rotor hits the fuselage, it may produce a downward directed force that adds to the weight. So one crude way is to slice the fuselage into small segments, treat each one as a cylinder, and then use the drag of a cylinder times the dynamic pressure from the downwash to compute the downward directed force. This is called the download. We also need corrections for main rotor, tail rotor interference. Because the tail rotor is operating in the wake of the main rotor. So the main rotor has got a downwash going this way. The tail rotor is sitting right in the wake structure. So one possibility is we need to correct for ground effects, all kind of drag components, hub, fuselage. We need an equivalent flat plate area, antenna, petard, hinges, latches, steps. Everything will cause drag. So this F is a catch-all number which will catch everything together. Remember we said normally we use 1/2 rho velocity square times CD times S, where S is the reference area. For aircraft, S is clearly defined, the wing area. For the fuselage, it's not so clearly defined. Therefore, rather than CD times S, they call the product into F, which is an equivalent flat plate area. Here are some characteristics aircraft. Very small, lightweight aircraft to heavy aircraft. And here are the typical equivalent flat plate areas normalized by the rotor disc area. Notice that many things are contributing to it. And fuselage is 1.5. The hub alone is costing 1.2. So, fuselage is a big thing. Hub is that little piece sticking out on top of the fuselage to which we are connecting the rotor. Can be very high drag. Notice that hub drag is contributing a significant amount. Anything that's sticking out will cause drag. For example, tail surface, of course, can cause drag. Antennas, you name it, everything can cause drag. So in the project, I will give you the equivalent flat plate area, but you do need to have an understanding of where these things are coming from. So when you are operating very close to the ground, remember the rotor disc, the velocity is V. At the ground, normally it should be 2V according to the model by Glovert, not modeled by Rankine and Froude. But if you're at the ground, the velocity in the far wake is 0. Therefore, you get a reduction in the induced velocity in ground effect compared to the out of ground effect, which is the Glovert model, which is the Rankine model. So the higher above you are, this reduction disappears. You approach 1. So this is the distance above the ground. This is the rotor diameter. This is a curve fit. Okay. So if Z is very, very high, this number goes away. You get 1, roughly 1 by 0.99. If Z is small, then you get a reduction in the induced velocity, therefore reduction in power. So power needed for vertical climb is sum of main rotor power, tail rotor power, power needed to raise the potential energy of the vehicle, and also any transmission losses and insulation losses. This total will be compared against the available power. So when power required equals power available, that means you cannot climb anymore because you don't have any energy left for rate of change of potential energy, then you have reached the absolute ceiling. On the other hand, if you can climb at a rate of 100 feet per minute, then you are operating at a service ceiling. So these calculations are normally plotted as charts. So let's do a quick example. This is like a helicopter, like a Black Hawk. The rotor radius is 27 feet, gross weight is 16,000. These are the various parameters: main rotor chord, solidity, number of blades, RPM of the velocity of the tip. Tail rotor is spinning. And the distance between the main rotor and tail rotor shafts is given as 32.5 feet. We are going to use for CD 0.008, kappa is 1.15, we assume there's a 10% loss in the power because of all those things we talked about: transmission losses, inlet losses, exhaust losses, compressor bleed losses, auxiliary power losses, you name it. Okay. So 10% is gone. So we are asked to compute the absolute ceiling as a density altitude. So this can be done using a spreadsheet or a MATLAB code. First thing you would do is you will correct the density ratio. This works if H is in International System of Units. I recommend that you just use standard atmospheric tables to find the density ratio and use it. Then the power scales with density ratio. So if you know information at sea level, you can find it at any other altitude. Now let's look at how would we do it. You pick an altitude H, look up the density at that altitude, then do the following. First, for the main rotor, find the main rotor area pi r square. Induced velocity is t over 2 rho square root a half. Then kappa times tau times v is the induced power. Then you'll take sigma times CD naught over 8 times tip speed squared times disk area. Tip speed Q times disk area is the profile power. Add it, that'll be the total power. So after you get the main rotor total power divided by angular velocity in radians per second, the main rotor torque. Now the tail rotor has to provide thrust to overcome this torque. So that's why you use the distance between the two rotor shafts to get the tail rotor thrust. Once you know the tail rotor thrust, repeat the calculation just like you did for the main rotor. Find the tail rotor induced velocity, tail rotor profile power, and then add these two things together. Compare this available power. Keep increasing altitude until required power equals available power. So if you do that, here are some details of the calculations. Pick several altitudes, several density, that area does not change. Induced velocity increases as the density decreases because it's inside the square root. Solidity does not change, omegas, these don't change. Then the main rotor power, profile power plus induced power is this. Torque is profile power divided by omega in radian. Then the tail rotor is this torque divided by this distance separating the main rotor shaft and the tail rotor shaft. Once you have the tail rotor thrust, find the tail rotor induced velocity, then do the same thing for the tail rotor power just like you did for the main rotor power. Add the tail rotor power and the main rotor power divided by 550 to get this in horsepower. Compare with available power. Note that the available power is decreasing because the density is decreasing. Then whenever these two things are roughly equal, then you have reached, in this case, within 18, so you have reached the absolute ceiling. To do the service ceiling, you'll take power available minus power required by weight. That will be in feet per second. Convert that into feet per minute. So whenever you have 100 feet per minute, somewhere between here and here would be your service ceiling. So you may need to refine it for 1150, 11,500, 11,600 to see when do you get 100. We are going to do some detailed worked out examples. So this is an example of how you would do service ceiling and absolute ceiling for a Black Hawk-like helicopter. In this problem, we have assumed the weight of the vehicle. Okay, so everything was done for a fixed weight. But weight can vary because you may have less passengers or lesser crew, military crew on a Black Hawk. They may be carrying different payload. They may be carrying different amounts of fuel. So depending on the mission operation, the gross weight can change. So it's possible to, for each gross weight, For a standard day, you'd use the standard atmospheric density. For a hot day, you will take the atmospheric pressure, standard atmospheric pressure, P equal to rho RT to correct for the density. Okay. So you get two ceilings, one for a standard day, other one for the hot day. Hot day, you have a lower density, therefore you can't fly that high because your power is decreasing, available is decreasing, your induced power is going up. Once you have, you can also plot this rate of climb as a function of altitude or as a maximum rate of climb as a function of gross weight of the vehicle. Then it's plotted as shown in here. This is for a given weight. As the altitude increases, the rate of climb decreases, as I have shown it in here. As the altitude increases, the rate of climb is decreasing. So all kind of graphs may be developed just from the hover performance. Power required, power available, you name it. Now we go to the forward flight performance. Forward flight, as we talk about, was induced power, which is kappa times thrust times velocity, profile power of the main rotor, same thing with tail rotor, then the fuselage parasite drag times forward power speed. So you'd have to add these two, all of these components together. For a given altitude, you change the forward speed. So this is best done in a spreadsheet or in a MATLAB code. Then you'll get for different gross weights or different altitudes, you'll get different curves. Okay. So the higher the altitude, the higher this power required. On the other hand, power available is dropping. So at some point, the power available curve will touch the power required curve. Then that's your service ceiling. Absolute ceiling, I should say. Okay. So again, you could use graphs like this, power required, power available, rate of climb, and look at ceilings in forward flight. What are these lines? This means even though you can fly very fast because of power availability, let's say your engine is very powerful, you can fly at this velocity. If the rotor is severely stalling, vibrations set in, fatigue life is decreasing, so they may not let you fly at this faster than this speed. So there may be other limitations on forward speed based on either the severe stall or even a light stall. Okay, so the operators may be limited in how fast they can fly, not because of power is not there. There's plenty of power, but the rotor is beginning to stall. So how do you find a maximum forward speed? Select a gross weight, atmospheric density, density ratio. Use the engine data to find the power available at sea level. Multiply by density ratio to find the excess power needed at higher altitudes. Do basically power available to power required. When it's reached, that's your maximum speed. So it can again be plotted in a number of ways. We don't need the lift to drag ratio in our performance, so I'm going to skip this. Now we are going to look at the range of a helicopter. How far can it travel? It turns out that you first compute something called a specific range. That's a distance travel per pound of fuel. How many nautical miles can it travel per pound of fuel first? This is called a specific range. Okay? So, for example, if your power required by the helicopter is known, then the fuel consumption, remember it is pounds of fuel per horsepower per hour. So you know for a given power, how much is the fuel being burned per hour. Then you can do the calculations as shown in here. Okay. So this is the fuel flow rate from all the engines. Okay, if you have two engines, each one may be producing half the power, but so each one will have a fuel flow rate. But when you double it, you're going to get back the fuel flow rate. So you look at the fuel flow rate in pounds per hour per forward speed. For each and every forward speed, you have a power of a helicopter multiplied by specific fuel consumption. That's going to be your fuel flow rate. So you want to find the best of the best value. So it turns out for the best range is where this touches it, because you're flying the fastest and you're burning the slowest amount of fuel. So you have a chance of staying up in the air longer, traveling faster. So draw a tangent to the curve. Basically, you can take the ratio of the fuel flow rate divided by weight for forward speed and see which is the maximum value in a spreadsheet, for example. Once you have it, that's called specific range. This value is specific range, 1 over slope. Okay, that means this distance by this distance, forward speed divided by fuel flow rate. Then it's of course a function of gross weight. So usually we do it for an average gross weight. So this power curve, the power needed curve is generated not during the takeoff, not during the landing, but somewhere in the average. So once you find a specific range based on the average weight, then you multiply it by gross weight at takeoff minus gross weight at landing. That's the range you have traveled. I will do some numerical examples. We will use this equation and hopefully it will become clearer so that you could do your project. People sometimes want to know the payload range. Basically, they plot for various payloads. The higher the payload, the higher the gross weight, then the shorter distance you can travel. Lower the payload, for a given gross weight, higher the fuel, so you can travel farther. So many things affect this. Why is this 28,000? Perhaps because you have a lot of payload or you have a lot of fuel. So depending on that combination, we would need to use the amount of fuel which determines the change in the gross weight to determine the range. So it's roughly a straight line as we've shown in here. Because of this approximation, this SR is found at the average weight times gross weight at takeoff minus gross weight at landing. So that's how we compute the payload versus range graph. Finally, we want to know how long it can stay up in the air. For example, you may want to do a loitering, you may want to do search and rescue, you may be doing an observation reconnaissance in a particular target area. So you want to stay up in the air. Then you draw the power versus forward speed curve. Find the minimum most power. That's your minimum fuel burn rate. That power times specific fuel consumption is the fuel burn rate. So take the time equal to change in the weight, which is power times specific fuel consumption. So you could inversely write it as specific fuel consumption per power. So per unit power. Okay. So then again you can integrate it. Then that's how you'll find the endurance. Again, take an average value at the average gross weight. Find the specific endurance, which is 1 over fuel consumption in pound per hour. Then multiplied by the change in the gross weight. Then you got the endurance. Again, we will do a numerical example. I'm going very, very fast at this point, but we will slow down when we do a numerical example. We are just developing the formulas, keeping them stored somewhere. Finally, if somebody wants to know the rate of climb, draw power available, power required curve. The difference between the red line and the blue line is the excess power. The excess power by gross weight is the rate of climb. So this excess power should be in a pound force times feet per minute. This should be in pound force. Then you get the answer in feet per minute, for example. So where do you get the best rate of climb? At this point. not in hover, not at here, but here. So here you have lots of excess power that you could use to climb up in the air. So again, these could be plotted as altitude versus gross weight, absolute ceiling, service ceiling for different gross weights, and do other things with it. So we have kind of quickly summarized all kind of formulas for computing the maximum forward speed, rate of climb, range, and endurance, service ceiling, absolute ceiling. So we are going to show some numerical examples. Right now it's a bewildering array of formulas, a ton of formulas here and there. Which one do I use where? Could be very confusing for you. So we are going to walk through several examples in our future videos, which will be our last set of videos before you start on the helicopter project.